we'll move on to the next issue in computational modeling of lithium-ion battery. A very important issue, or probably the central issue, is how do you determine the equilibrium voltage? Okay, that is voltage under open circuit condition. Okay, there's no current that is passing. It's a charged battery before it starts getting discharged. Okay, so that's an important thing. Or equilibrium voltage. Okay, this is an important measure for if the computations are meaningful. They have to compare well against experiment with respect to equilibrium voltage. So how do you define equilibrium voltage? It boils down to the thermodynamics of the system, right? So delta G is equal to minus NFE, right? So that's the fundamental equation from thermodynamics. So you write it as equilibrium voltage is, in this case, cathode minus chemical potential of lithium at the anode divided by Z is 1 for, okay. Okay, so let's understand this. So what is that we are trying to say? If you understand this, I mean, chemical potential sometimes students do not have a feel for chemical potential. Let's even simplify this equation, okay? So typically, entropy, okay, for most cases, G is equal to H minus Ts, right? G is equal to, free energy is equal to H enthalpy minus Ts. H is equal to U plus PV, okay? So for the systems we are considering, both this term and this term are small, okay? So you can approximate G by U, that is internal energy, okay? So why is there a potential in a battery? Because you have, let's say, anode, lithium initially, the charged state, lithium is in the anode at a higher energy state, and there is a cathode here. Okay, lithium, the chemical bond, lithium is forming some chemical bond, either or it can be just lithium metal or lithium intercalated within graphite or bound to silicon or tin or so on. Okay, so in whatever the case may be, in the charged state, the chemical potential of lithium at the anode is higher than the chemical potential of lithium at the cathode. That is, when lithium goes from the anode and to the cathode, the bonding becomes more favorable. Okay, so this is delta G. Okay, delta G is exothermic. Okay, so this exothermic change, the favorable bonding as lithium goes from anode to cathode, is what gives rise to potential. So when you do that, there is a bit in the charged state, lithium is concentrated in the anode. For example, lithium intercalated with graphite, which is the most common anode, and there's no lithium in the cathode. This energetics, this delta G, is a function of concentration of lithium at the anode and lithium at the cathode. Okay, so as the battery gets discharged, the concentration of lithium at the anode decreases, and the concentration of lithium at the cathode increases. Okay, so this V we are calculating is concentration dependent concentration of lithium at the anode and cathode dependent, and dependent on the charge state. At what stage of the battery discharge we are talking about. It depends on state of the battery. In fact, state of charge. Okay, state of, this is a term you might hear. SOC. Okay, so for example, in a lithium and lead acid battery, okay, which you might have seen, the density of the electrolyte is a measure of state of charge and so on. Okay, so here, as the battery goes from completely charged to fully discharged, the state of charge changes. So this is something that so this potential which you get can be integrated. Okay, so it depends upon the state of charge. And you can talk about an average potential for this delta G for this reaction by the potential you generate is Z is the depends on the charge that is transferred. Okay, so this is just like the electrostatic equation. Okay, uh, uh, okay, so this delta G is equal to minus NFE, right? It's just like an electrostatic equation, except that G and E are thermodynamic variables. They are not mechanical variables, as in the case of electrostatics. This we mentioned in an earlier lecture also. All right. So let's, there are, you may, okay, so for example, let's just write it in the form of the most common cathodes are transition metal oxides. Okay, so in terms of reaction, if I have to write, okay, so the reaction which we are talking about um, is like supposing lithium intercalates. Okay, so that is intercalates means it's a layered oxide. Let's say you have layered oxides, and what do you mean by lithium intercalation? Lithium goes in between layers, or there is this layering helps in diffusivity, facile diffusion of lithium within the cathode. Okay, so that's why these layered oxides were favorable. So the reaction which we are considering is lithium, the energetics, which is important, is lithium goes, there are three compounds which we have to calculate. For example, this can be the lithium that is intercalated as lithium. You take a lithium, let's say this is the anode initially, and at that stage, the state of intercalation at the cathode is this compound. And then this lithium, as it is added here, it goes to this composition. All right, so all these equations are, I'm just following the notations in the paper so as to make it easier. So as I said, because TS and PV are negligible for the case under consideration, when X1 is greater than X2, that is, I'm adding lithium to this compound to get to this stage, I can write the equilibrium potential in the following way. Okay, so what are the, if you do a DFT calculation, what are the calculations which we need to do? Okay, there are actually three calculations at any particular state of charge. You have to do a calculation of lithium at a particular concentration at the anode. Then there is lithium at a particular concentration at the cathode. Then you add some more lithium so that the concentration of cathode increases and the concentration. So there are two calculations for the anode and two calculations for the cathode. Okay, so that's the way you have to do this thing. Okay, for example, this can be lithium metal or lithium reservoir. Okay, so this can be, instead of lithium in the intercalated state, it can be lithium metal. Okay, we can talk about chemical potential of lithium in a lithium metal foil. Okay, so we can also talk in that manner. All right. Okay, so that's the way we talk about. So you will hear this term intercalation versus conversion electrodes, conversion or displacement. Okay. Okay, so there are two kinds of cathodes which we are talking about, or two kinds of electrodes in general. So in one of the cases, in the case of intercalation electrode, there's typically a layered structure. Okay, so if you take anode, graphite is the most common layered structure which you've seen from lead pencils and so on. Okay, so there are layers. Typically in graphite, for example, there are covalent bonds within a layer, and there are certain kinds of interactions. Okay, so van der Waals interactions and so on between the layers. The layers can move fairly easily with respect to each other, and there is some space in between the layers where lithium can get intercalated. Okay, this is not only for graphite, which is just carbon, even for transition metal oxides, transition metal sulfides, such layered compounds are possible. Okay, so that's an important breakthrough in lithium-ion batteries, is identifying such layered compounds. Okay, so that is a common material geometry that you hear. Okay, and there's also other case. Okay, so which is first demonstrated in a big way by the group of Tarascon. Their group is one of the Tarascon. It's a French Jean-Marie Tarascon. Okay, so a large, strong group in experimental battery work. So they demonstrated, for example, in the first time they demonstrated was they had, for the cathode, they had nano-sized cobalt oxide. Okay, cobalt oxide. So when lithium gets to the cathode, so what happens is, typically, what do you think? Lithium might just get intercalated in the cathode. Okay, that's not what is happening. Actually, what is happening is there's like a chemical reaction. This is called conversion electrodes. Okay, so cobalt oxide gets reduced to cobalt, and the oxygen from cobalt oxide goes to lithium and forms lithium oxide. Okay, so on the other side, you have, let's say, lithium metal foil. At the anode, okay, this is what is happening at the anode. This is what is happening at the cathode, right? The cathode. Okay, so the overall reaction this is still exothermic, okay? So if you just from chemical intuition, you can see this is going to be an exothermic reaction, and that's what is going to give rise to battery voltage, okay? So so you would anticipate the rate of reaction, okay? This might not be that facile compared to a rate of lithium intercalation, okay? So it had some promise because it is nano-sized, okay? This is nano-sized cobalt oxide, okay, that had some promise, but that has not really given rise to very new battery chemistry, okay. So but a lot of work has been done, continues to be done, okay, in this case. But you should, at least the important thing is, you should not suddenly get uh, puzzled by this use of two kinds of electrodes, okay. So let's look at what is being predicted, okay. So just maybe before going into that, going into the real comparison, I will talk about one particular thing, okay. So right now, see, if you look at DFT, okay, Hornberg and Kohn said that energy given the ground state density, let's say in this case electronic density, the energy, there is one-to-one correspondence between density and uh, energies. Okay, so then that's Hornberg-Kohn theorem and Kohn-Sham. Okay, so first Hornberg, there is HK theorem. Which showed that energy is a unique functional, right, of electronic densities, right? So they showed that. Then Kohn-Sham approach gave what is that? You were able to represent the entire system is like Hartree method. Okay, so you were able to express the electron occupancy is in orbitals. So that gave an expression for kinetic energy. Okay, so from quantum mechanics the operator for kinetic energy. So you had Kohn-Sham approaches, you had Kohn-Sham orbitals, from where you could get kinetic energy. Okay, the kinetic energy of the system is well defined. Then still what is open is how do you determine the exchange correlation function. Okay, even now the central approximation are in the forms of exchange and correlation potential. Right? What do you mean by that? Electrons are fermions, right? So when you went from Hartree to Hartree-Fock approach, you introduced something called Slater determinants, which incorporated the fermionic nature of electrons. And so each Slater determinant is indicative of a particular configuration, right? And if you want to, so that is, but in a real system, the system is actually not in a single configuration, but is in multiple configuration. And for each of this configuration, electronic configuration, there is a different Slater determinant. Okay, so that is, we'll go into this. Okay, so we'll do a separate lecture on this, but just to give a context, I'm going to make some few issues and then get back to talking about batteries. Okay, so exchanges, fermions, and Slater determinant. this is correlation is need to have multiple slated determinants. Okay. In DFT, you do not have slated determinants. Okay, so this is not there in DFT. Okay, so that itself, so the exchange is not correctly calculated. The fermionic nature of electrons is not correctly represented in density functional theory. So it is like you just have Kornsham orbitals, like Hartree orbitals. Okay, so that's the way DFT represents electrons, incorporates the occupancy of electrons. So that is an approximation. And then it obviously, as soon as you don't have slated determinants, there is no question of having multiple slated determinants, okay, to represent correlations correctly. So because of both these issues, we have some approximations for calculating exchange correlation function. Okay, there is, you heard this in the previous lecture. There's something called local density approximation, generalized gradient density approximation. Okay, so all these things introduce an error called self-interaction error. See, if you incorporate this exchange correctly, certain cancellations occur. That is, the electrons do not interact with, the same electron doesn't interact with itself. Okay, there's like a jargon. I will do a separate lecture on the whole slide. I will do a separate lecture so that it's more clear. But just a preliminary introduction. There's a second preliminary introduction, if you remember, because in the MIT OCW lectures also this was talked about. And there's a second introduction. There is something called a self-interaction error. A lot of effort has been going on to correct this problem. Okay, so this is a big error. Not a big error, this is an error that has to be addressed. So typically the electrons are more delocalized than they really are. Okay, for example, certain things which are insulators are, the DFT predicts them to be, when you compute, it shows the computations suggest they are metals. Okay, that's because of an error. Okay, so this is the main error right now people are trying to address, and there are lots of approach. You may hear something called DFT plus U. Okay, that is computationally relatively computationally cheap. People have been trying to do that, and there is something called hybrid functions. So people think both these things are in some ways ad hoc, okay, but people, it has worked. Okay, it's a practical approach to addressing this problem. We'll talk about this, okay, in a later stage. So this is still an issue that is becomes more and more important to transition metal oxides. Okay, so let's get on, and then so if you look at the okay, so this GGA, okay, the LDA is the simplest form of approximation. Then LDA, then you have GGA, then you have more and more expensive methods. Okay, hybrid functionals. Because more accurate most of the time than DFT plus EU and so on. This doesn't introduce too much additional computation time, but hybrid functional does introduce a lot of computational time. Okay, so what is that we are plotting here? For lithium, intercalation potential is plotted on the y-axis. Okay, so in effect we have calculated this particular quantity. Okay, so at a particular state of charge, or maybe this particular quantity for different transition metal cathodes. Okay, so these are very common. LCO is the most likely the cathode you have on in your battery is LCO. That was the battery cathode that Goodenough first worked, okay, which gave him the Nobel Prize. All right. And then you typically, how is battery research, experimental research is conducted? Uh, Typically, you explore, you synthesize and measure, take measurements over a range of cathodes. Okay. The two common cathodes are, this is what is called LCO. Okay. This is another common cathode. Okay. There's a good chance that your battery, cell phone battery might also have this particular cathode, LFP. Okay. Lithium ion phosphate. So what is being plotted are this intercalation potential uh, as a function of computation. Okay, these are all computations. When the lithium is bound to these cathodes, how does the intercalation potential change? Okay, so this is just that gives you a measure. Okay, so as you can see, there is a lot of variation. Okay, variation of 1.2. That is, in this red is GGA, GGA plus U or DFT plus U. Okay, so this is what is called DFT or LDA plus U. Okay, I will talk about what is this U. It's called a Hubbard parameter. We will talk about this. Okay, in a later lecture. So as you can see, there is for some cases. In this case, there's not too much difference, okay, between these three approximations. These two are more or less computationally they scale at the computation. There's no much increase in computation time, okay, between GGA and GGA plus. So, but HSC is more accurate in most cases, but the cost of computation increases significantly. Okay, but it is important. Okay, so because this change, look at this change, 1.2 is a significant change, right? We can get things very different results. Okay, so so there's something that you have to be aware of. So this can also be a good topic. Okay, for example, what do I mean? What are the different ways of addressing exchange correlation in within DFT? That's it's a slightly advanced topic than what has been covered, will be covered in the class. Okay, so this is you should be aware of that, and I would do one more lecture on this particular topic at a later stage. So we will wrap up this lecture